Good morning and welcome to this course on the foundations of continuum mechanics. Today we will be talking about matrices and determinants. In this topic we will focus on some special matrices, matrix multiplication, and we'll talk about determinants of matrices. So we'll be focusing on the use of indicial notation as always to study these topics. So let's get started. So the first question we have to answer is, why do we need to discuss matrices in this mathematical background on tensors? Tensors, as we have seen, especially the second order tensors, are represented using matrix notation. So we have seen in the past that a second order tensor sigma is sometimes represented as the matrix sigma 1 1, sigma 1 2, like this. So since tensors are represented as matrices, so we need to understand how to deal with them, especially with the use of indicial notation. Vectors also can be written as matrices. In fact, we have been writing, such as for example, a vector V as a matrix which is containing just one row, V1, V2 and V3. So that's a 1 by 3 matrix, whereas sigma was a 3 by 3 matrix. In fact, there are situations where we require to evaluate their determinants as well, especially if you are trying to prove things using indicial notation. So let's take an example. So we have an equation written in the indicial notation as Ti equals sigma ij times nj. If I was to write this in the symbolic notation, this would be the vector T is the dot product between a second order tensor sigma and a vector n. This is an important equation. This is something we will discuss in a lot of detail when we talk about stresses in a couple of weeks from now, but for now let's keep into the mathematics. So if I write this equation in an expanded form, this is what we get. So this can also be written in a matrix form. So this is the matrix form. Now we can definitely see that this equation in the indicial notation was definitely more compact than writing it as three equations or in the matrix form. So definitely indicial notation is something that we tend to prefer. But today's discussion is not about that. Today's discussion is about how to focus on this form, that is the matrix form. So let us first talk about some special matrices. A unit matrix, which is written as I, which stands for identity. Sometimes we also write a 3 by 3 to denote it's a 3 by 3 matrix. It's given as 1 0 0, 0 1 0 and 0 0 1, which, as we already know, can also be written as a delta ij. So if you put I equal to j equal to 1, you get delta 1 1, which is a 1, delta 2 2 and delta 3 3 are also 1, and all other indices are 0. So this is the indicial notation of the representation of a unit matrix or identity matrix. Now whether delta is actually a tensor or not is something we'll address later this week, but for now you can take it as a matrix. So the other matrix we deal with is called a null matrix, where all the elements are 0. Another one or another type of matrices we deal with are called diagonal matrices or a diagonal matrix. So in this matrix, only the diagonal terms are non-zero, all other terms are 0. But the diagonal term can be different. So typically we denote them as lambda 1, lambda 2 and lambda 3, and the other elements are all zeros. So we'll be dealing with matrices like this. In problems, you'll read that there's a diagonal matrix or there is a unit matrix, so we must understand the meaning of these words. Next is the idea of transpose of a matrix. So I'll say the topic heading is special matrices or matrix operations. So the transpose of a matrix, let's say a matrix is A, so its transpose is given as, so what we notice is that, let's say the element A12 moves to this location in the transpose matrix. Similarly, the element A13, which was the third element in the first row of A, now moves to the third element in the first column of A transpose. Similarly, the element A23 moves to the second element of the third row in A transpose from the third element in the second row of A matrix. In the indicial notation, we can write this simply as the I comma jth element of A transpose is simply the j comma ith element of A. So now that we have talked about some special matrices and matrix operations, let us talk about matrix multiplication. So if we have a matrix C, which is a 3 by 3 matrix, which is a multiplication of another 3 by 3 matrix A times a 3 by 3 matrix B, we can write this in the matrix form as, so the element C11, for example, which is this element, is simply the multiplication of the first row of A to the first column of B. Let's use the same color. So I can write C11 as A11 B11 plus A12 B21 plus A13 B31. Now using our indicial notation, this can be written as sum k going from 1 to 3 A1k BK1. Now this is C11, which with our summation convention or the Einstein notation can simply be written as A1k times BK1. So the sum over the index k is implied here. Now if I want to express the index, the general term Cij, all I need to do is I need to write this as Aik Bkj, and you can check that this works for all the elements of the matrix C. So this is the general way to write the multiplication of two matrices A and B, which is equal to C. We must note that the second index of A is equal to the first index of B, and this is what allows multiplying a row of A to the column of B. So these Aik and Bkj are simply numbers. So what that means is I can write this as Bkj times Aik. That's also exactly the same thing, and you can try it out. You can expand this over k, and you can see that the values are, I mean the expression is exactly what we had here for I equal to j equal to 1, but it works for all values of I and j. So the ordering of A and B does not matter in this notation. However, the ordering of the indices in A and B, that is important. You cannot write Aik as Aki, that will be incorrect. But you can move around A and B, and that will not change because Ik and Bkj are simply numbers when you expand this expression. We also see a resemblance of matrix multiplication with inner product. Let's have a look. So if I was to write an outer product between matrices A and B, that will look something like this. So AIK, B, Q, J. You can see all the four indices are different. So the order of this tensor is 4 because we have 4 free indices. Now if I apply a contraction on this by making K equal to Q, then we get an inner product, because inner products are obtained from outer products by applying contractions. So this inner product is AIK BKJ, which we can see has 2 free indices because K is a repeated index now and the order is 2. So let's try a problem to get a better understanding of the notation in matrix multiplication. So the problem says that we have to show using indicial notation that if C equals AB, where A, B and C are matrices, then C transpose is B transpose A transpose. So let's try it out. So let's write in the indicial notation. So C equals AB can be written as, in the indicial notation, as Cij equals Aik times Bkj, as we just saw. Now the relation between C and its transpose is simply that Cij is the j comma ith term of C transpose. Similarly, Aik is the k comma ith term in A transpose, and Bkj is the jk term in B transpose. Now what do we see here is, if you look at the repeated index k here, we say the first index of A is the second index of B. So I'll just reorder these terms for convenience, but the meaning is still the same. So B transpose jk times A transpose ki. That's the j comma ith term or ji term of C transpose. And also, again, for convenience, although it's not required, I will change the indices. I'll replace I with the j and j with I because they're all dummy indices. So this becomes B transpose Ik times A transpose Kj. And this is simply C transpose equals B transpose A transpose, because the second index of B is the first index of A. So that means that we are multiplying a row of B transpose to a column of A transpose. So that completes the solution. So let's try another problem to further improve our understanding of matrix notation. So in this case, we are required to show that identity times A equals to A. So let's prove using or show using indicial notation. So the left hand side in the indicial notation is, it's a I and K, I and A are multiplied, they're both matrices. Let's say they're 3 by 3 matrices in this case. So this can be written as delta Ik A K J. That's how we write matrix multiplication using indices. And now we can use the substitution property of delta. So this becomes A I J. And what is right hand side? If I write the right hand side in the initial notation as well, then the right hand side is A I J. So I can see that both LHS and RHS are the same. So that again completes the proof. So we will now talk about determinants of matrices. So if we have a matrix A, we can write its determinant as det A, which is represented as a mod of A, which is the determinant sign, and then we write the elements of A. But this is just a sign. What it actually means is that the determinant of A is, there are different ways to do it. We'll expand it over the first row of A. So it's A11 times the 1 cofactor, that's C11, plus A12 times C12 plus A13 times C13. So C11, C12 and C13 are cofactors of A. Again, we have chosen the first row of A to expand it, but you can also expand it over first column or some other row or column. So the cofactors are the I comma jth cofactor is given as minus 1 to the power of I plus j times the I comma jth minor of the matrix. So I'll just write the complete expression for determinant. So this becomes minus 1 to the power of 1 plus 1. So that's coming from C11 times A11 times M11. M11 actually is, so if you're writing the first minor, what you do is you take this matrix. So basically, if you're doing 1 1, then you block the first row and the first column. So whatever is left, you take the determinant of that. So this is determinant of so this time we block the first row and the second column. Then lastly, this. So this is how typically we have been evaluating determinants till now. But now we have a more elegant way to work with determinants, and this is through the use of indicial notation. So in the indicial notation, the determinant of A is given as epsilon ijk A1i A2j A3k. Now we can see that this is again quite compact. We don't need to write or expand over the rows or the columns of A by writing the minors and so on. And this is very helpful for simplification. So I'll box it because this is a very important indicial notation relationship for us, and this helps significantly with simplification. In fact, there are problems where you don't have any determinants, but still you can use these ideas to prove tensor or indicial notation relations. So we'll be doing that through the tutorial this week. There's another way to write this. So we can also write the determinant of A as epsilon ijk A I1 aj2 ak3. So you can use any form you want to evaluate the determinant in the indicial notation. So let's try out a problem. So the problem says that if we swap any two rows of a matrix, the sign of the determinant changes. So we have to show this using indicial notation. So let's take a matrix A and another matrix B where we have swapped the first two rows of A. The third row of A and B are the same. So what we have to now show is that determinant of B is negative of the determinant of A. So let's do that using the indicial notation representation of a determinant. So let's see what the determinant of A is. So determinant of A is epsilon ijk A1i A2j times A3k. So this is the determinant of A. Now let's write the determinant of B. This is the determinant of B. Now the meaning of B1i is if you put I equal to 1, you get B11. I equal to 2, you get B12. I equal to 3, you get B13. So this denotes the first row of B. Now we know that the first row of B is actually the second row of A. So this can be written as A2i. Similarly, the second row of B is the first row of A. And there's no change in the third row of B because that's the same as the third row of A. So this becomes epsilon ijk A2i A1j A3k. Now what we'll do is we will change the order. So I will move A1j to the left and A2i to the right. And this is completely allowed because A1j, A2i and A3k will ultimately expand to numbers. So it doesn't matter if you have scalars or numbers, you can multiply them in any order. They're all commutative. The multiplication is commutative. So this can be written as the next step is to do some replacement of indices. So we see that whatever index of the first epsilon, the first index of epsilon is the second index of the second A. Similarly, the second index of epsilon is the second index of the first A, and the third index of epsilon is the second index of the third A. So as long as I maintain this order, I can have any indices I want. So I'll replace and the first index, the second index of the first A with I. So this red one becomes the second index of epsilon. And then for the second A, I will have a J. So the blue one is a J. And the third index remains as it is. So there's no change here. All right. So now what we'll do is we will try to bring this into an epsilon ijk form. So we know that epsilon ijk is the negative of epsilon Jik, because they are different cyclic orders. So this becomes epsilon Jik becomes a negative of epsilon Ijk. Then you have an A1I, A2J and A3K. If we compare this with the expression for the determinant of A that we had here, you can see that this is nothing but simply the negative of the determinant of A. So we have proved what was asked from us, that determinant of P is the negative of the determinant of A. So I'll just summarize again that we have learned a very powerful expression, that is to express the determinant of a matrix using the indicial notation, which includes an epsilon, that is a permutation symbol. So we haven't proven it, we just wrote the expression today and we learn how to use it. But as a problem in the tutorial, I will show to you that we can get this expression for the determinant using what we have learned till now. So this will be proved or shown through a problem in the tutorial later this week. So this brings us to the end of this lecture. Today we learned about matrices and determinants and how we can express them in indicial notation. We did a couple of problems that involved matrix multiplication and evaluating the determinant of a matrix. So these are important topics and you must remember these expressions for the determinant of A or determinant of any matrix for solving problems, either directly related to determinants, or in some cases you may use these ideas to express a quantity as a determinant and prove a relationship. So before we close, there is a problem for food for thought. So the problem says that can we write determinant of A, which is epsilon ijk, ai1, aj2, ak3, as epsilon ijk, aj2, ai1, ak3. So can we swap the first and two A terms in the expression for the determinant in the indicial notation? So please think about it and I'll see you in the next lecture. Thank you.